You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists who are going to shine a light on our topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronic What's Up podcast. Today's discussion comes from our application note. It's on ringing. So what happens when you have ringing in your electronics? Well, ringing is a very common term. It refers to the undesired oscillation that happens when a power semiconductor switch turns on or off in the presence of parasitic inductance and capacitance. Energy stored in the parasitic junction capacitance of the switch is released during the switching transition and rings with parasitic inductance coming from the stray fields of discrete power inductors and the wiring inductance of the PCB traces, component leads, connectors, and more. Now, in real circuits on real circuit boards, parasitics are always present, which means all switching converters produce at least some type of ringing. This electromagnetic interference, or EMI, is typically in the range of 50 to 200 megahertz, and at these frequencies, PCB traces and the input and output leads act as unwanted antennas that result in both conducted and radiated noise. Most switching converters operate at frequencies of 5 megahertz or less, and their switching harmonics are typically very low in power by the time they reach 50 megahertz, so ringing shows up in radiated EMI scans as a separate fundamental noise source. While the switching frequency and its harmonics can be filtered with discrete LC filters at 50 to 200 megahertz, many filter inductors are no longer inductive, but in fact have become capacitive and provide little to no attenuation. Likewise, the filter capacitors are often inductive in the 50 to 200 megahertz range. Ferrite beads are far more effective because they have very low resistance at low frequencies, but they have high resistive losses from about 10 megahertz up to 1 gigahertz or more, depending on design and construction. Ferrites are traditionally employed in series with the input and output connections of switching converters and can also be placed in series with the power switches. You can see this example in our attachment 1 of this podcast. The main disadvantage of placing ferrites in this way is that heavy currents pass through them, so the devices must be rated to handle the dissipation from these currents in their DC resistance, and also the dissipation as they convert the high-frequency ringing currents into heat. The dissipation from the high-frequency currents is often difficult to estimate or even simulate since the waveforms depend almost entirely on the parasitic elements. So in practice, a ferrite bead is typically selected with a rated current that's 2 times the actual max current that will flow through it. At low power, cost-effective surface mount devices can be used, but as power increases, multiple large ferrites may be needed in parallel, and this can consume board area and increase cost. In this podcast, based on an application note, we'll show how small 0603 or 0805 sized ferrite beads can be used to reduce the slew rate of the high-side MOSFET's switching transitions in a synchronous buck converter, which in turn reduces the amplitude and the duration of the ringing. Specifically, slowing the slew rate gives excellent results while increasing the switching loss only slightly. This task is normally done by carefully selecting and tuning a resistance in series with the gate of the MOSFET or in series with the positive supply voltage of the gate driving circuit. However, a ferrite bead of the same size as the resistor performs as well or sometimes even better, and it can be selected from product datasheets with far less time spent on the lab bench. In our next attachment we call Figure 2, we show two possible positions for a slew rate limiting element. First, we have in series with the high side MOSFET's gate, or in series with the Bootstrap. Now the Bootstrap position is superior for three main reasons. First, it only limits the rising slew rate, so this saves power since only one switch transition is slowed during each cycle, and switching loss increases when slew rates are decreased. Second, slowing the falling slew rate of the control MOSFET in synchronous buck converters can provoke shoot through. Now this is where both MOSFETs are on at the same time. This is not something you want. Third, the Bootstrap pin is accessible to the user for most buck regulators with internal MOSFETs, making this technique applicable to many more control ICs. So how do you select the proper ferrite bead? Well, for our example circuit, we are using DC501A demo board using the LTC3703 synchronous buck controller from Linear Technology. Step-by-step instructions and images will be made available as attachments in this podcast. Our first step needs to be to measure the ringing frequency. So starting without any slew rate limiting elements, set up the converter with the typical input voltage and maximum output current. In our example, these conditions are 48 volts in, 12 volts out, and an output current of 6 amps. Then capture the rising edge of the switching node, making sure to set the oscilloscope to its full bandwidth. For best results, use the spring tip accessory supplied with most oscilloscope voltage probes. This helps to minimize the pickup of radiated energy in the loop created by the probe tip and the grounding pigtail. A section of three 2.54 millimeter spaced breakaway header pins with the center pin cut off actually makes an excellent test jig. Also, a piece of 0.5 to 0.75 millimeter bare wire wrapped around the exposed barrel of the voltage probe. It'll work well if the spring tip is lost or missing. You can find our example in Figure 3. Zoom in with the oscilloscope until the period of the ringing can be measured. For this example, the ringing frequency is almost exactly 150 megahertz. Next, calculate or measure the average bootstrap current. You can see in our calculation for the average bootstrap current for the high side power MOSFET in attached Figure 4. For this example, the converter runs at 260 kilohertz, and the datasheet for the SI7852DP power MOSFET lists a maximum gate charge of 41 nanocoulombs. Considering 1% of the total time period as rising time transition, to pump maximum gate charge to 41 nanocoulombs, the average current during on time of the MOSFET is around 5.3 milliamps. The bootstrap current waveform also includes transients due to the MOSFET switching of 1 amps or more. These are typically less than 100 nanoseconds in length, so their contribution to heating of the ferrite is minimal and they can generally just be ignored. Our next step is to select the highest resistance ferrite at F ring. The Worth Electronic WE-CBF family of surface mount ferrite beads ranges in size from 0402 to 1812, and the high volume production of the 0603 series makes them particularly affordable. If you need to go even smaller, you can always try the WE TMSB series. These are tiny 0201 ferrite beads. Despite their small size, even the member of the 0603 series with the highest resistance at 150 megahertz can handle an average current of 50 milliamps, making it more than capable of handling the 5 milliamps of drive current from our previous example. Figures 5, 6, and 7 compare the original circuit with no slew rate control to the insertion of the standard resistance at 16.2 ohms. The ferrite bead, an 0603 size device rated 600 ohms at 150 megahertz, and then another ferrite bead, also 0603, and rated 2200 ohms at 100 megahertz. At 150 megahertz, the resistance is approximately 1500 ohms. Next, we'll select and use ferrite beads for ringing control in switching converters. The device with the highest resistance at the ringing frequency actually provides the best reduction in both the amplitude and the duration of this unwanted oscillation. And selection is really a simple matter of consulting the product datasheets. Figure 8 shows the typical reactance, resistance, and impedance curves for the 600 ohm and the 2200 ohm ferrite beads. Make sure to use the resistance curve, since true resistance is what actually converts the high frequency current into heat. And finally, review the power loss and dissipation. Slew rate control is a trade-off between reduction of EMI and increasing losses. Slowing the switching transition too much can cause the power MOSFET to overheat and can also lower the overall power efficiency to unacceptable levels. Section 4 of our application note shows the response of the DC 501A evaluation board to EMI scans as per the European standard for EMC in IT equipment. You can view these radiated scans by clicking on the attached link. Overall, the radiated EMI scans support the data taken in the time domain. A well-tuned resistor placed in series with the Bootstrap circuit's positive supply reduces both quasi-peak and average radiated power levels by about 10 decibel microvoltages, but a ferrite bead selected for the highest resistance at the fundamental noise frequency works just as well, and often better than the resistor. Slew rate control can be applied to the gate pins of the other switching converters, but special care and attention must be taken when placing any type of slew rate controller in series with the gates of the MOSFETs or IGBTs. Other topologies with high side switching include the 2-switch forward, half bridge, and full bridge converters. For all of these topologies, the gate controller should be placed in series with a positive supply of the floating gate driver. However, each of these topologies also includes at least one low side switch, and the boost, flyback, forward, and even push-pull converters all use low side switches exclusively. In general, the rising edge requires control, and the falling edge should be allowed to slew as quickly as possible. In most cases, the best solution is to add a small Schottky diode in parallel to the slew rate control element and connect both to the gate. To wrap it all up, ferrite beads placed in series with a Bootstrap pin of buck regulators can make excellent ringing control components, and when applied properly, they can be used to treat the source of the high-frequency noise without taking up too much of the PCB area and without large sacrifices in power efficiency. Their benefits over tuned resistors include ease of selection and reducing testing time in the lab needed to actually design them in. While the 0603 ferrite costs slightly more than an 0603 thick film resistor, the improvements in EMC more than pays for itself in forms of smaller, lighter, cheaper filters at the inputs and outputs of the switching converters. Snubber circuits placed in series or in parallel with the switching elements won't need to dissipate as much power. This also improves power efficiency, keeps temperatures lower, and saves both money and PCB area. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.